All right, guys. In this session, we are going to cover actually one of the most influential papers in the world of generative AI, transformers, and so on and so forth. It is the BERT paper. This paper it spawned a whole family of models to come up. The sentence semantic search is actually founded upon, the sentence BERT paper is founded upon the work that this BERT paper has done. And so we are going to read this paper very carefully. Right? The background that you need to understand it is the original, the classic attention, the transformer paper. Attention is all you need. If you recall, we did attention is all you need last time. I will give you a very quick recap of what we did there, and then we'll get started. Give me a moment to situate myself with the writing board. So here is a quick recap of what we did with the attention paper. See, the attention paper said it was an encoder decoder. It was sequence to sequence model, encoder decoder, text, a cow jumped over the moon, right? All of it would go through transformations. It would become token IDs. It would become word vectors. Position vector would be added. All of those things, I won't recap that whole territory, but it would go through an encoder, right? And then what you would get are your, let me just say, encoders produce the latent representation, the hidden representations of this H1, H2, HK. And then they would go basically into a decoder model, which was also autoregressive in the sense that decoder would produce a token, a word, and that word would be back-fed in. Whatever it would produce, there was an autoregressive nature. Remember, you would feed back in. For example, the best way to think about it is that if I have text as input, I have an encoder and I produce a hidden state. Let me call this X, hidden state X. Then I have a decoder. If all that the decoder got was the hidden state, inherently it would produce the same word again and again and again, same output again and again. The only way you can produce a different output, let's say that it produced an output O1, is if you took O1 and fed it back into the decoder along with the hidden state, right? So then it produced O2. Then you would feed both O1 and O2 back into the hidden state, and you would continue doing that. Does that make sense, guys? Yeah, because then the input to the decoder keeps changing. It is the hidden state along with whatever it is that you have produced. So that was your attention mechanism. What the BERT paper says is that let us primarily focus on this part. Focus on the encoder part and see, let us look at the core value proposition of this thing, the hidden state that came out. What can we use it for? Are we together? But then there is a question, how do you, if I remove the decoder, how do you train just the encoder itself? Right? Now you have taken half the transformer away. You just have the encoder part. How would you train this machine? So that is what this paper is about. The history of this paper is people were trying different things. For example, there were people who were throwing the encoder away and looking only at the decoder because they were focused on the generative part. GPT crowd, the GPT train. There was Elmo and so forth. So there's prior work that was being done. And somewhere around that time, this paper, this landmark paper came out in 2018, actually. I don't know, it's 2019. It's a later revised version for 2019, but this paper was quite a fast follow after the transformer paper, right? And represented the first big rethinking uh, in the field of transformers, or breakthroughs in the field of transformer. So what it said was quite interesting. It said, let us give it two sentences. Are we together? We will give it only the encoder bit. We'll give it sentence 1 and sentence 2, and then put a some sentence boundary. Demarcator. Right. Now, you might say, why do I need a sentence demarcator? Aren't punctuations enough? Well, multiple reasons. Because, first of all, many languages don't have punctuations. Then, secondly, the definition in natural language understanding of a sentence is very vague, right? A whole paragraph could be a sentence. Remember, I told you that sentence, the way it's interpreted in natural language, is not the way that you would expect it to be in normal, grammatically correct form of writing. Sentence is any bit of text. It could be half a sentence. It could be a real grammatically correct sentence. It could be many sentences. It could be paragraphs. It could be the whole document itself, right? And so you need some token, some boundary between them. What it also did is that it prefixed it with a special token called CLS. Why would you do that? We'll come to it in a little word. A special word you would prepend it with, the first sentence with, called CLS. And you'll see why. So now it played a game. It played a very interesting game. It said that, see, the sentence 1 itself is made up of tokens. For example, it could be the cow jumped over the moon. And sentence 2 could be another sentence. Happy cows were grazing in the field. Right? 2 sentences. So what it says, and that's where the word bidirectional encoding comes in. It says that, treat it like a normal transformer. What will a normal transformer do? Every single word will go pay attention in every direction. Will pay attention to words before and words after it. Does that make sense, guys? And therefore, bidirectionality is in fact inherent to a transformer unless you prevent it. Unless you put some masks and say, don't look ahead. Right? Only look back. Are we together, guys? Right? So you let it, so that bidirectionality comes inherently. But what is the game? They played a very simple game. They said, okay, we need to train this transformer. Now, I will tell you, it has multiple methods to do it, but the one that has survived, and in fact, was in a subsequent paper called, in a subsequent improvement, Roberta. You notice the word Bert in there? Roberta. They showed that actually one of the methods is good enough. And in fact, better to use just one method. So I'll teach you that one method from this paper. What they did is, they said that, let's take a sentence. The cow jumped over the moon. It's a sentence. Now, to train a model, inherently, what do you need? You need an X and a Y, input, output. Right? And you make a model predict the output, some form, right? This is your typical supervised learning, isn't it? You give it an input, you know the output, you look at the output the model produced, and your loss function is derived from Y. the gap between yi and y hat, or the degree to which y hat is not yi, isn't it? So for example, if you're, so now the thing is, how do you train a transformer? Those days, you were still talking about hundreds of millions of parameter model. And in 2018, that looked ginormous, right? Wow, such a big model, hundreds of millions of parameters. It looked crazy big. How in the world do you train a model that big? You need a lot of data? Well, Google said, well, that's what we are. We are the search engine of the world. We have scraped the web. We are full of data. But now, trouble is, all you have scraped is a lot of text. How do you create label data? So this is label data, right? Label data means for every xi, you know the yi. Labeling data has always been horrendously expensive. Some human being has to sit and label the data, isn't it? So obviously, you might be rich in data, but you're not rich in label data. Nobody is rich in label data, right? And so came the question, you scratch your head and you say, how can I magically transform the vast oceans of data that I have somehow into label data, right? And they had the simplest and the cleverest of ideas. What they said is, we'll play hide and seek. What we'll do is, we are going to mask one word, right? And what we will give it as input is the mask jumped over the moon. So this is my X, right? And my Y is, this machine somehow needs to produce the word, guess the word cow, right? So it shouldn't say the calculator jumped over the moon, right? Or the river jumped over the moon, or something silly. It should say the cow jumped over the moon, right? So whatever, somehow I need to create a machine in which, now can I create this data? This is easy to create, right? All you're doing is you're masking a word here or a word there. And whatever word you're masking becomes the Y. Does it make sense, guys? This trick used to have a formal name in natural language understanding called closure. Close. Nobody uses the word, actually, to my knowledge these days. People just call the masking model. Masked model, trained with masking. Common sense, right? Masking. So what you would do is, you can now, you say, well, we have a winner now, because this kind of data is extraordinarily easy for us to produce. We are the Google. We have scraped the whole web, the world. And so we can produce bazillions of such labeled data, isn't it? Everywhere we find a sentence, mask a word or two, right? And they mask 15% of the words. And let's say, for simplicity, assume one word. But actually, in reality, it's more technical. It's 15% of the words. And you make the machine guess those words, right? Come again? Okay, similar ideas, but yes. But let's stay focused here. So now the question is, but what about this? When you give it to an encoder, you give it the sentence, the cow jumped over the moon. Even if you go and replace this word with a mask, fact of the matter is, I will end up with how many vectors? Let's think. 1, 2, 3, 4, 5, 6. And then there's a full stop. 7 vectors, right? So I'll end up with H1, H2, H3, H7, isn't it? Right? So now I need to predict somehow, create a Y hat, which should be some string. Let's say a horse. I need to somehow from these vectors produce a prediction into a string vocabulary. So that is easy. Let's work our way systematically backwards. So the vocabulary, let's say that you choose a vocabulary of 30,000 words, right? So the word starts with, I don't know, aardvark. I mean, most of you have taken GRE at some point in your career, so you would remember that. And let's say the Zephyr. How many of you remember the meaning of aardvark? Yes. Good, you remember it. You have a bright person here. Come again? Yeah. So, and then this. So let's say this is 1 all the way to 30K. Now, what you do is there is a trick called softmax, right? You give it to, you feed it into a neural network. You can pick any one vector as input. Let's say a vector, HI as input through a network, a feed-forward network, a simple softmax, and you produce a probability for each of the word. This is the softmax. Softmax. Probability of aardvark all the way to probability of Zephyr. What really matters is when you're talking of cow, the probability of cow. Right? Isn't it? So the two questions remain. So, okay, I can use a softmax and then I can create a loss function easily because I can say, and this is the loss function. If I know that the answer is cow, yi is cow, then all I need to do is take the probability of cow produced by this machine, right? It is called negative log loss. So I'll give you a bit of intuition of why negative log loss. See, a good machine should have guessed the word cow. It should have said cow, 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 probability 1. Calculator, probability 0. Isn't it? If you say probability of cow is 1, what is the, it is correct. So how much mistake do you make? 0. Isn't it? You have made 0 mistake. So loss is 0 at that moment. How do you convert 1 to 0? One easy way is take the log of it. Log of 1 is 0. So no loss. Lovely. Well, suppose you say 90% probability. Suppose you say 90% probability that it's a cow. Well, you're not quite sure. You still have a bit of learning to do. Right? Because your eyes are still going towards the zebra. Who knows? It must be the zebra or the buffalo. Buffalo looks closer. It may be the buffalo. Right? Well, you still have some learning to do. Am I making sense? So now, how do you quantify and say probability of 0.9 is not so good? Let's think about it. We want it to become a positive loss. Let's go a little bit further. Suppose it said probability of cow is, I'll take a number, 0.1. Now your loss should be even bigger. So the smaller the probability value, the bigger the loss. How will you make that happen? So one way, and I'm just giving you an intuitive answer. There's much more rigorous mathematics behind this. But if you take the log of a probability, what is the log of a fraction between 0 and 1? If log of 1 is 0, log of, let's say, a 10 is 1, or let's say in base 10, or E is 1, what is the log of something smaller than 1? It has to be less than 1, less than 0, right? It has a negative number. That seems to serve a purpose. Except that we don't want the negative. We want the loss is positive, right? We measure it to be, have made CS mistake. And the smaller the probability, the bigger the loss. And we know that the log of a small number is a pretty negative number. The log of 0 is minus infinity. This seems to serve our purpose, except that we need to convert the minus into a plus. How do we convert the minus into a plus? Add a minus sign here. Right? This is it. And therefore, the loss is calculated as negative log likelihood. Right? So all you need, so now we have a game. All we need to do is from the text, we pick up these things. Xi is some sentence with a mask. The yi is cow. And so yi had the only thing you care about is probability of cow, isn't it? And therefore the loss is loss for the ith term, for the ith data instance is minus log probability of cow. Does this make sense, guys? Do you see how common sense it is? Math, therefore, is the most easy thing to understand if you just see how to reason with it. Is it making sense? By the way, this has a very scary and fancy name, negative log likelihood loss function. Has anybody heard that scary term? Negative log likelihood loss function.
Yeah.
Right. Well, that's it. That's all it is. I just gave you the intuitive understanding of that loss function. But now comes a trick. This is all fine and dandy, but now wait a minute. I am looking at so many vectors coming out. I need one vector to push into the machine. I can't push more than one vector. So which vector to pick? There is no reason to pick any one vector, isn't it? So what I can do is I can say, hey, let's do one thing. Let's always prefix a special token, right? And whatever the hidden state of the vector representation of the hidden token is, we will feed that into the softmax, the CLS token. And it is called CLS now, as you can imagine, for very obvious reason, because CLS is a short form of classifier, right? Because what do you want this machine to do? Predict what word it was. It's a classification task, isn't it? It's a classifier task. And that's why the token is called the CLS token. Is it all making sense now? And so you play this game, find what word I hid. So I'll tell you something. 1 second. I'll tell you something. When my kids are very, very small, my daughters, I have 2 daughters. So, you parents, you try all sorts of tricks to teach them. So when I was trying to teach them, very, very young, I was trying to teach them ABCD, right? So what I would do is I would tell them that I really don't know it. They would try to teach me ABCD, and every time they taught me, I always seemed to get the order wrong, right? So I would get it. And I remember my elder daughter, she was very, very concerned. How in the world will we teach Papu ABCD? Right. And then what she would do is she'd put the letters there and then cover one of them and ask me, okay, what is there in the sequence? Which letter did I hide? Right. And then I had to guess. Right. And she thought she was teaching me to know the sequence of letters in the alphabet. And this is exactly the same game. Actually, what my daughter discovered as a 3-year-old, before 3-year-old, is exactly this trick, isn't it? Cover a word and ask, okay, what did I hide? And she was trying to teach me the alphabet by hiding a word here and a word there. Yeah. So that's it. In her case, it's a letter, not a word, letter in the alphabet, asking me to guess what did she hide. Right? So, well, it turns out that her dad, Papu, did finally learn the alphabet eventually. So this is how you have the alphabet learned. So now let's read this paper. No, CLS is just a token you add. So any token you add, the machine will convert it into a vector. Every token becomes a vector. That's it. Whatever token, whatever the CLS becomes, You use that. So you don't feed any one of this. You feed the CLS token into your softmax. No, you literally have a token called CLS, the word CLS. And why is that relevant? So why would you? So multiple thing is there is no preferential picking the first word or the last word, because sometimes the meaning of a sentence is there very much in one word than the other. You don't pick any. You just put a placeholder, random token, which has no meaning. And see, it has to do with the heart of attention. People, words, meaningful words will pay different attentions to different words, other words, isn't it? But a word that has no meaning, the attention that it pays to the whole sentence is not derived from its meaning, right? For example, the word bank may pay attention to the word river because it's a river bank. But a word CLS has no meaning. It will therefore pay attention to the whole sentence. And the idea is it will therefore contain the essence of the whole sentence, isn't it? That's the point. Right? So you feed that CLS token into the softmax, and what do you get? You get this machine which makes predictions. Do you see that? The beauty of this machine. So now let's read this paper. This paper is considered one of the most landmark papers. Actually, I wanted to check how many citations does this paper have. Let's find that out. I haven't checked actually. It's been years since this paper, I do read every time to the students, but I read it originally so long ago, it must have accumulated a lot of bird paper archive. Let's go here. So it was there in October 2018. Let's look at the number of citations. Do you see that? I don't think it counts above 9999, right? It's only 4 digits. Stops counting after that, right? So you can imagine how influential and foundational this paper is. So please pay attention as I explain it. The sentence bird, the whole sentence encoding, is that paper rests upon this paper. Right? And the whole semantic search, ultimately, foundationally, you have to start with this paper. So let's read this paper very, very carefully. Isn't it fun to write a paper that breaks the citation limit? Right? So we will look at this paper. So guys, do you have fresh minds? Are we all fresh here? Pay attention. It starts actually as typical research papers do. It doesn't start with hyperbole and so forth. Papers are very formal and understated. So you have to parse through it to see the real importance of what they're saying. We introduce a new language representation model called BERT, which stands for Bidirectional Encoder Representations from Transformers. Let's unpack this. They speak of encoder. Well, encoder, because there is no mask attention, it is inherently bidirectional, but they wanted to emphasize it for a reason to distinguish it from other things like GPT, etc. Right? So it is bidirectional encoder representations from transformers. What are those representations? Those H vectors, the states. In particular, here, it will be the H of the CLS token, the hidden representation of the CLS token. Are we together? So that's the meaning of the first sentence, if you unpack it. Unlike recent language representation models, blah, blah, BERT is designed to pre-train deep bidirectional representations from unlabeled text by jointly conditioning on both left and right context in all layers. Now, this might look like some esoteric mantra, so this one needs a little bit of deciphering. Let's go over it very, very slowly. The sentence matters. It is designed to pre-train. What does pre-train mean? To explain pre-train, and I have to explain to you what transfer learning is. See, as models became bigger and bigger, and it was already happening in computer vision, People were creating CNNs before this. Remember, this is 2018. Transformers were just taking off. In the field of computer vision, CNNs were the king of the hill. If you remember the history of the field, there were all of these things: ResNet, AlexNet, VGG, right? Do you remember Inception? All of this bigger and bigger convolutional networks were coming up. Those networks took a lot of compute to train. And so what people used to do is they would train that on vast amounts of image data and compute resources, right? And then release the model. They have done the best they could do on the public data. So let's bring this concept of transfer learning a little bit, a digression into that. So you would take lots of data, train a model on it, right? And C, release it. So it, for example, became very good. An image model became very good at looking at a picture and saying, this is a house, that's a cat, right? And that's a giraffe, things like that. Classification task. When you could do that, then what people would do is they would take such a model, and suppose they want to instead use it to specifically tell two things apart. I'll take a special use case. They want to tell whether they are looking at a weeping willow tree or a pepper tree. Those things are common here, guys. Do you know the pepper tree and weeping willow tree? If you want to classify between a pepper tree and a weeping willow tree, you can download this model and just use it out of the box. And it may do very well. But suppose you want further refinement, right? Suppose you want to tell with much higher accuracy whether it's a pepper tree or a weeping willow than the accuracy of the model you just downloaded. What could you do? You could give a special data set which contains only these two things, labeled data, weeping willow, pepper tree, and further train the vision model, right? You could fine tune. So you could fine tune release it, let others fine tune the model to specific use cases. Are we together? They can fine tune it further. And to fine tune, what people found is that because a machine that can understand what a tree is, what a house is, what a dog is, much of the work is already done, isn't it, of training the machine. You don't need too much data to fine tune that machine to know the nuances, the specific nuances that differentiates a pepper tree and a weeping willow to a slightly higher accuracy. Am I making sense? Right. Because it has learned a lot. It just needs a little bit more knowledge. So that became fine tuning. So when that began to happen, these things, there was a word coined, I believe it was Fei-Fei Li here at Stanford coined the term foundational model. This word was coined fairly recently here, a foundational model. And this process that you just saw is pre-training. Pre-training, and this part is fine-tuning, tuning to some specific use case. But when you pre-train a machine, you don't just expect that it is the only way you can use it is you have to fine-tune. The expectation should be that in a vast majority of cases, the foundational model will just work out of the box. Are we together? Today, we take it for granted. We just set up Olama on our machine, download a LLM, and start using it. No, we don't say that, no, I need to first fine tune it. Most people don't. They just use it as it is. Am I making sense? So that is the concept of transfer learning, whose two stages are pre-training a foundational model and later fine-tuning it for a specific task. But a good foundational model is inherently, it has the qualities of a good foundational model. What are the qualities of a good foundational model? A, should give usably good performance on a variety of tasks, isn't it? So that speaks to its versatility. Versatile. It should be versatile, isn't it? Do we understand what versatile means? Should be versatile. Then the second quality is should be easy to fine tune with much smaller data. So I might take just 100 examples of pepper tree and 100 examples of weeping willow and fine tune it. That's all, to make it better at the task of telling a find apart. Or I could be more specific. For example, I might look for diseases specific to a pepper tree, right? Plant diseases. So I can show it a picture of only a pepper tree, healthy pepper tree, and a pepper tree with a specific sort of a hump or burl or whatever it is, protrusion in the plant trunk, tree trunk, that represents a certain disease. And now I have a disease detector. Practical uses, you can fly a drone looking for trees that are infected. Right? Trees are prone to fungal infection. You guys probably know that in the Appalachian Mountains, for example, majestic trees, majestic forests have disappeared for as little simple a reason as just a fungal infection. Things that have lived for thousands of years, just poof, gone. Right? So that's how it is. Just like civilizations disappear, forests disappear. So you could use it. So that's just an example of a use case. You could do that. Right? So I introduced multiple concepts, the concept of transfer learning, the concept of a pre-trained model. Pre-trained model takes a lot of data to train a foundational model, right? Right? And then fine-tuning. So now, in view of that context, let's read this sentence again. Unlike recent language representation models, so forget that part, BERT is designed to pre-train deep bidirectional representations from unlabeled text. Let's focus on that part. Designed to pre-train. So what is the idea? You're trying to build a foundational model. You're pre-training it. Deep means what? Well, lots of layers of the neural network. Today, we don't even bother to use the word deep. It's assumed. With these big models, deep neural networks is assumed. Right? Trained bidirectional representations. Why? And Coda anyway does bidirectional representations, isn't it? From unlabeled text. And that's the interesting word. The moment you say unlabeled text, you can train a model, you would say, no, wait a minute. How can you train a machine? How can you do a supervised training of a machine by just giving it text, but not giving it labels? Now, why? Just giving it xi, but not x, but not y. So that's a mystery. But I've already explained to you how they do it. But in the paper, they just in the beginning start. And they say by jointly conditioning on both left and right context in all layers. Jointly conditioning on both left and right means what? The word looks both ways, left and right. right? Isn't it? It searches for its meaning both by looking at all the tokens before and after. Now you may say, well, of course, that's what encoders do, don't they? And so, coming from the previous uh, transformer talk, that would look sense. But see, in that time, this had a context for why they were saying it. We'll leave it alone. Let's move forward. As a result, the pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for a wide variety of tasks, such as question answering and language inference without substantial task-specific architecture modification. What are they saying? If you train a foundational model, at the end, you can attach softmax, you can attach whatever you want, last layer, to later on to do a whole variety of tasks. Right? So it's a quality of this model that they often give you headless, means the last layer is chopped off just so that you can screw in whatever head you like to do whatever task you want. Right? So today, this all looks common sense, but obviously it's important to state it. BERT, and here's the powerful thing, BERT is conceptually simple and empirically powerful. It obtains new state-of-the-art results on 11 natural language processing tasks. And this thing is, when you read it, you stand back and say, wow, what happened? There are many, many different tasks in natural language processing, like question answering, telling whether it's a cow or a duck, the classification, sentiment analysis, this, that, many, many natural language tasks. You're saying that one model, it achieves or it completely shatters the record. It becomes a gold medalist on 11 different tasks in natural language processing. How many tasks are there? Well, 11 of the most important tasks. All the most important things. In everything you have in front of you, it goes and takes the gold medal, effectively, in common sense language. Now, you would be surprised, right? If one of your athletes came out of nowhere, went to the Olympics, and just acquired 11 gold medals, was that versatile as a sports person, you would be thoroughly impressed, wouldn't you? And that's pretty much what is implied by this paragraph. Came out of nowhere as a dark horse and became a gold medalist. So what is it? So now you want to know, what is it? So this is it. We'll go into it. Language model pre-training has been shown to be effective for improving many natural language processing tasks, blah, blah. These include sentence level tasks such as natural inference and paraphrasing, which aim to predict. I won't read the rest of it. I won't even read much of the paragraph, but I'll just go to the crucial paragraphs. They say that we argue that current techniques restrict the power of pre-trained representations, especially for fine-tuning approaches. So what they're basically saying is that it's not a good idea for many, many things. In particular, they talk of OpenAI's GPT, the original GPT, which they say for many of these kinds of tasks that they will work at, which are based on good representations of text, those things don't do well. Why? Because GPT is a generative model. It is not good at representation, it's much better at generation. Because GPT is a decoder-only model. Like this model, I said it works on the encoder part of the transformer. GPT actually takes only the decoder part of the transformer. Right? So that's the thing. So what the main thing it does is BERT uses something called close task, which is the mass language, right? I won't go into it. Related works, forget about it. What it does, what the previous models did, doesn't matter. Here they say using the CLS token. Now, the important thing is mass language model. This is the task. Train it using mass language. The next sentence prediction, like the other task you can do is, if I give you a sentence, remember BERT takes two sentences, right? So I can ask you this question. Does the next sentence follow this sentence, or it is a non sequitur, irrelevant, right? So if I say it was the best of times, it was the worst of times, it sort of goes together. But if I were to say it was the best of times, the carburetor failed to work. Where did that come from, right? It's a non sequitur. So basically, you're telling whether the two sentences have any connection. Does one follow the other or not? Right? That sort of thing. Later on, actually, the work of Robert, etc., showed that it's unnecessary to do task two. Not only unnecessary, if you don't do task two, actually, you can train the birds better. Right? So you do this, but the results speak for themselves, guys. Let me, not one thing, but many things, just about anything it touched, it broke the state of that. GLUE is the General Language Understanding Evaluation Benchmark, perhaps the most important benchmark in text, natural language understanding, GLUE. It tries to measure how well your machine has understood the language. Right? So what does that mean? See, guys, if I mask the word cow and I say the jumped over the moon, and it can correctly predict cow, what is the implications of a machine being able to correctly predict the word cow in this context? Surely it cannot do that unless it has natural language understanding. It has understood human language and its structure. Would you agree? It has to understand human language before it could, out of the 30,000 words, zero into the word cow and say, that is what should be here. We're getting it, right? And GLUE is a benchmark of that. So let's look at the GLUE score for BERT. BERT, they built two models, base model and a larger model, right? Their large model by today's standard would still look relatively small, but this is 2018. Look at this. Compare it with GPT of those days. You can clearly see that, or other models, Elmo and so forth. Do you notice that just like that, even the base model achieves state-of-the-art performance? Do you notice that, guys? Look at any column you like. Any column, pick one column. Which one should I pick? Let's pick this cola. What do you notice? The 52 and the 60, the BERT large, hands down beats everything before it, isn't it? So when you have a benchmark that comes out so good, a model that comes out so good at so many, then there's a squad question answering database. And it turns out that in question answering also, if you give a question and an answer, it will tell you whether the answer actually answers the question. Right? That sort of thing. All of these things, you can go look at different benchmarks. I won't go into that. They're benchmark after benchmark. But basically, when you have a model that does that, you know you're looking at something. In today's language, we would call it a foundational model. Right? Now, you realize that what is the difference between this and the sentence BERT that we started the course with? A sentence BERT is just a BERT that has been trained with a with a contrastive loss, triplet loss, with a contrastive loss at the end of it, isn't it? Because what are you doing? You take a BERT and you're giving it text. You're taking the HLS, the token, and then you are just taking a vector, H vector, and you're basically saying that given a text, T, a similar text, and a random text, make sure that the cosine between T and S is max, and minimize the cosine between T and random. That's all it is, right? But you're just using BERT. And that idea leads to the whole world of semantic search. So you can imagine the tremendous influence that BERT had. BERT went and revolutionized pretty much large swaths of natural language understanding. Actually, with this BERT coming on to the scene, and with attention, people knew things were happening. BERT coming in, suddenly people knew, okay, if you go back and look at the YouTube of those days, suddenly you find articles coming. that RNNs are dead. It's all BERT. It's all transformers now, right? And for sure it is. Today you don't use, at least the old style RNNs, you don't use anymore in natural language understanding. It's more or less wiped out. They're making a comeback, but there is a new age, sort of a new generation variants, things that sort of is reminiscent of RNN, Mamba and so forth. There's a, but they are completely different. Like they're very much more sophisticated. They try to take the best ideas of attention and RNN and hybridize them together. Jamba, for example, does that. So, but then that was the importance of BERT. So today you would call BERT a foundational model, right? So you covered, so how many papers that we covered? We covered attention is all you need. So now let's put the sequence because I taught you backwards to get you started and hit the ground running. We first did sentence BERT with the triplet loss. I just said, imagine an encoder that does it. Now you know what that encoder. Then I taught you the attention. Then I taught you BERT. The right sequence should have been attention, BERT, and then sentence BERT. Are we together? Now, there was a problem with BERT. BERT is huge. Well, by today's standard, it's hardly huge, but still huge. So people said, can we not have a smaller model? It is all very good, high performing, but our machines of those days can barely handle BERT. So can we have a baby BERT? Right? And so that brings us to the concept of distillation. But I think when I'm looking at your faces, you all look rather tired now. How many of you are in game for one more research paper? Or would you rather that we did it with a fresh mind next time? Next time, right? So next time, the concept that we will get into is distillation, right? But when we do the distillation, we're not talking about beer. We are talking about models, right? So we'll do that next time. All right, guys. So with that, I will end. I'll take questions and then end this session recording. Any questions on BERT, guys? By the way, do you see the elegance and simplicity of the idea? Just mask, hide and seek of sort. What did I hide? Mask something? Say, what did I hide? Yeah. Oh, remember, it goes through the attention layers. The whole point of that is each of the words pays attention to every other word, right? And it keeps going through that. So if you remember, the attention vector was the vector V J Q I K J square root of D softmax.
And each word converting to a vector, and that particular thing, the word converting to a vector,
Yeah.
how they do it, what man.
Yeah, then words become vectors, but when they go in, they become attention vectors. Attention vectors are also called contextualized vectors. Contextualized means they pick up some of their meaning from the adjacent words, from the other words. See, what happens is that, okay, let's go through so you have, so start with the vocabulary. Vocabulary will start with ard, walk, let's say, all the way to, let's say, zephyr. So let's give it a number, 1, 2, and this is, let's say, 30K. I'm just throwing in. By the way, these are not the exact correct values. You can look it up, right? Maybe is A, just the letter A is there. It will start there. But okay, let's put it this way. So now any word cow can map to some index, let's say 125. I'm randomly cooking it up. Huh? By the way, this probably is not true. 125, 125th word. Now associated with every word, so this is called the token ID. Now from the token ID, I can create a vector embedding. I know the vector representation of word vector in some d-dimensional space, let's say 300 dimensional space, right? I happen to know the vector embedding in some 300 dimensional space. How do I learn that? Actually, BERT learns it literally on the fly because of the mass language model. So there's a technicality, it's differentiable. So it back propagates and learns even the word embeddings in the process. But for simplicity of understanding, imagine that it looks it up in some place, right? So for every word, there is a vector, cow, I, there is a vector which lives in, let's say, 300 dimension space. Imagine there's a database for that, right? So what happens is for every token, every word in the vocabulary, there is a vector. That's it. Yeah. That is predetermined and you can look it up. At inference time is predetermined. In reality, what happens is that vector database itself is learned. The word vectors is learned in the process of training BERT. Right? So that's a bit of technical magic, Shashandri. And how does it do it? The answer to that ultimately goes back to the fact that if your model is fully differentiable, everything can be trained. Even what is the optimal word vector in the language can be trained. And once you train it, you store it. You just store it in some lookup table. And the moment you encounter a word, you can look up the word vector. So there is a word vector. Then the word vector, let me just call it the cow vector. Cow. Then you add to it the position of the cow in the sentence, the position vector of the cow in the sentence, you append it. So this will always be the same. You look it up in your database. But this will depend upon where that location is in the thing to get the total embedding vector, cow. In the transformer, you're passing in the embedding vector, cow. It will go through the attention layers, all this cross attention, and then will come out a hidden state for cow, which roughly speaking is the attention vector for cow. Right? One easy way to think is it's attention vector, but it's not really attention because what really happens is even if you first of all, there are multiple layers of attention, but within the attention, there's this glue, right? I call it the peanut butter and jelly. Like you don't put breads, like if I gave you 2 slices of bread and say, go eat it, you would frown and say, what? But the moment I put nice peanut butter and jelly, you say, okay, now this is good. Right? So I often intuitively give people the idea that before you put 2 slices of bread together or 2 slices of attention together, you always have to put peanut butter and jelly to make a sandwich, right? And the reason for that, the more technical reason, while that is an intuitive picture, the reason is that it is the feed-forward layers that bring in the deformation. See, the attention is KQV, etc. It's more or less a linear, except for the softmax. But it is the real deformation and the ability to adapt to anything is in the feed-forward layer. Also, there is emerging research recently that, remember I told you that the transformers remember a lot of facts? Actually, the research is showing that it is in the feed-forward layer that it remembers the facts, right? That simple, humble, dense layers or feed-forward layers where it remembers the facts. So you have a lot. So at the end of it, what happens is attention goes through various transformations and projections and dimensionality changes and deformations and whatnot. At the end of it, a hidden state pops out. Hmm. Mhm. Yeah. Oh, why do we have to do that? Yeah. Again, and why do we do that? So the basic idea is think of one unit, attention plus some feed forward as one head. What people realize is one head is doing great. So the natural question they asked is, if one is good, more is better. So, and today, well, and practically they realize that you can have multi-head attention, parallel layers, and this. So in reality, what happens? The reason you have multi-head attention, other attentions in parallel, is because they look at different elements of the sentence. One looks at the grammar, one looks at the semantics, and so on and so forth. So it's worth it because, again, the magic of back propagation is to create an efficient minimization of the loss. So it's worth it because, again, the magic of back propagation is to create an efficient minimization of the loss. So it's worth it because, again, the magic of back propagation is to create an efficient minimization of the loss. So it's worth it because, again, the magic of back propagation is to create an efficient minimization of the loss. People have to specialize. These attentions have to learn to do things differently. Otherwise, they'll be redundant. They do it. Now, why stacking the layers one on top of the other? What we are finding is this goes to the theory of representation learning. So if you are there in the Tuesday's class, Intro to AI, we go into that very deeply, but I'll summarize it in a minute. What happens is that at each successive layer, the machine is coming up with a deeper, more abstract representation of what it was given. It is learning more semantic depth from the previous input. That is the reason deep neural networks are so effective. The depth gives it an opportunity to come up with a better understanding, layer by layer of what's happening. Oh no! So first of all, how many heads to stack one on top of the other? Generally, uh, so the original architecture used 6, but basically now 12, 24 are pretty common. The general idea is that the training cost, it is the neural scaling law. The more heads you stack, the more parameters you have in the model, the more data you need to train, and the more number of cycles you'll need to train it for, the number of compute steps you'll need to train it for, right? So you stare at the data set size, you stare at how much hardware you have, time and compute budget you have, and therefore you use that to determine how big you want to make your model. Sanjay. Yeah, no, no, no. One multi-head in that 6 layer, one will look at the grammatical structure of the same sentence. The other will look at the semantic nature of the sentence. So they just look at different nuances. I'm just giving you an idea in understandable terms, but these are mathematical machines. What they are looking at is something really different, as different as possible. But sometimes it is a little bit hard to interpret. But what the original paper showed is that one head seems to be much more grammatically inclined, another head seemed to be more semantically inclined, another head seemed to be looking at something else, so on and so forth. You don't have to code it at all. The whole point is that the magic, and this is the magic of backprop and loss function, that it will force the machine to specialize and look at different aspects of the sentence. Yes, yes, yes. That's all it is. Yeah. Same sentence going to different heads, right? Right? It's fanning out to different heads, and each head will say, okay, I'll look at the grammar, I will look at the meaning, and things like that. That way, yeah. Yeah, that's how it is. Same sentence, yeah. Remind me your name? Ganesh, yeah. Mhm. Now, it pays attention to all of them without being colored by its own meaning. See, if I'm the word bank, I will inherently pay more attention to the word river, right? But if I'm a word without a meaning, I will have to pay attention to the whole sentence to figure out what in the world is the sentence saying. That's the intuition. Yeah. Yeah. No, it is trying to get the whole context, the entire context. That's the reason you plant it there. It's deliberately an imposter, which is impartial and therefore has to pay attention to the whole context. Are you all together, guys? Any questions, guys? Those of you who are remote, I hope you're still with me.
So, Asim, just a quick question, right? How does the head know that one needs to focus on semantic and the other needs to focus on? How do they decide,
No, it
what they?
doesn't. It doesn't, Manju. What happens, and this is the most beautiful thing. So imagine that. Okay, I'll give you an analogy. Two people have to build a nut and a bolt, right? And you keep it keep giving it pieces of metal and you say, make a nut, make a bolt. And every time they make a nut and bolt together, right? You look at the quality, how defective it is, and then you tell it that, no, do better. Would it stand to reason that after a little while, they will say that, hey, you become good at making nuts and I'll become good at making bolts? Even the slight edge, let's say that just by accident, there's a symmetry breaking. One guy does nuts a little bit better and the other guy does bolt a little bit better, right? What will happen after that? They will quickly latch on to the fact that there is an easy way to improve performance. I will keep making better and better nuts. You keep making better and better bolts because that is the quickest way to bring down the loss or the error, isn't it? And so it is literally like that what's happening. You don't tell these machines anything. You just say, I need loss to go down. Through backpropagation, sooner or later, there will be an asymmetry and one will latch on to one aspect of the job and the other will latch on to the other aspect of the job. And because they're playing, in effect, a cooperative game, the overall loss will go down much faster. They will do the job much better. And so what you will end up with is a great nut maker and a great bolt maker. And that is literally what's happening. And that's why you put different heads.
Thank you.
Mhm. Yeah, that's right. Exactly. Exactly. Yeah, it will figure it out internally. They will all learn to do the job better by specializing. You realize that nut and bolt example, the two guys managed to specialize. So these different multi-head towers, they learn to specialize, right? To do the same job better. Yeah, okay. Yeah, that's good. That's nice. So guys, are we getting that? Yeah, no, proprietary. They just, I mean, it takes so much effort. See, what happened is that this whole trend not to release model, this disease has started only very recently. And I would say it has sort of started with OpenAI, which has, the OpenAI is the closest of all companies you can imagine. The tradition within AI was that, see, think about it this way: to train any of these models is a environmental disaster. You realize that to train a foundational model today takes the same amount of electricity as would keep an entire small city going for a whole year. These are environmental disasters. At the end of it, when you create such a model, the general feeling was that we need to contribute it back to society because these are foundational models. Let people compete on the applications they build from the foundational model rather than whose model is better. This entire disease of holding your model secret has started very recently. Yeah. See, the foundational pieces people release, like for example, BERT, right? They're using this with maybe some, see, the small twists, small turns, and some proprietary, but the basic architecture is the same. See, where they get it right, search query goes through an entire ecosystem of products. When you give a search, somebody told me that it goes through at least 50 to 100 pieces of technology. Any one of those pieces of technology, right, 1,000 pieces of technology, any one piece of technology is actually well understood. The, the secret sauce is how well they have fit it all together, right? To a large extent. And they might have a couple of very proprietary things they don't talk about, but generally in the AI community, it has been a high tradition to be very open about the research. You'll be surprised that most of these research papers are coming from these big houses like Google Mind, Google DeepMind, Google Brain, and Meta, Microsoft, etc., etc. These and the research universities and so forth. These have been the ones very openly taking the whole field of AI forward. Uh, it is sad to say that that trend now is turning, and see, every country has two opposing cultures. If you look at the United States, there's a culture of open research and open source software, very vibrant. There is also a culture of very close proprietary, behind the door secret sauce making. And uh, both of these, they produce some things are best produced by closed systems, some things are best produced by open systems. And if you look at, for example, the other dominant technology power, China, they literally have a word. I believe the word is shenzai. Anybody from China can convince shenzai. They just say share everything openly, right? So one of the ways, for example, the Shenzhen, the city that is just next to Hong Kong, took off. It was 30 years ago. Actually, the history is very interesting. I'll just stop the recording and